Alright, we're going to pick up our electrochemical cells introduction. Go ahead and cross out practice 2. They've removed questions like that for the AP exam. You're asked to identify oxidizing and reducing agents. You're not asked to rank them in order of strength, and that's just one I missed and meant to take out. Alright, so moving into practice 3, they're giving us half-cell reactions, and they want us to figure out who's the anode, who's the cathode in order to make it a galvanic cell. And so that right there tells you, okay, this has to be spontaneous, so I have to make sure that my E0 cell is a positive number. And so you notice they're both gaining electrons, so both of these are reduction reactions. So we know that one is going to have to be flipped because they occur in pairs. And so the question is, which one do we flip? If we were to flip the first one, then this reaction becomes a positive 0.23 volt. And when I add that to a positive 1.23 volts, I get a positive number. If I were to flip the second one, now I'm going to have to make this a negative 1.23, and the overall voltage would be negative, which means it would not be galvanic. So that's how you figure out who you flip. So I'm going to flip that one. So now we've got nickel forming nickel 2 plus 2 electrons, and E0 is now a positive 0.23. So I'm going to get rid of that one so we don't try to use it. Alright, I like labeling which reaction is which because that's going to keep you from making a mistake later. So this one is gaining electrons. Electrons are on the reactant side. So if it's gaining electrons, that's being reduced. And this reaction is losing electrons or producing them. And so this one is your oxidation reaction. And so to get E0 cell, it's just a matter of adding these two up. And so we get a total of 1.46 volts. They asked us to identify the anode and the cathode as well as writing the balanced overall net reaction. Well, if I look here, I've got a problem because I've got 4 electrons and 2 electrons, and that's not going to work. So I'm going to have to come through and multiply this reaction by 2. Now, we don't multiply the E0 by 2, only the reaction by 2. So we get 2 nickels plus 2 nickel ions and 4 electrons. So to get the overall reactions, I just add them up. So my 4 electrons cancel, and I get O2 plus 4H plus 2 nickel form 2 nickel ions and 2 waters. And for identifying the anode and the cathode, we know that oxidation occurs at the anode, and so our anode would be the nickel, and our cathode would be the oxygen side. So we can't have an electrode made out of oxygen gas, so we would have some sort of inert electrode like platinum, and so the O2 side is our cathode. Alright, for our second reaction, we've got Ce plus 4 going to Ce plus 3. That's a positive 1.7 volts. And then we've got another reduction reaction that's negative 0.14. So again, to make it galvanic, I've got to make E0 cell be a positive number. And so I certainly can't flip that first one, but I can flip the second one. And so then I would have 10 forming 10 2 plus and 2 electrons. And the E0 for that is now a positive 0.14. So again, we'll get rid of that one. Alright, so our E0 cell is just the sum of those two things, so 1.84 volts. Alright, for our overall reaction, I've got 2 electrons. I only have 1 electron, so I've got to come through and multiply this reaction by 2, but I do not double the E0. I add the 2 reactions up, my 2 electrons cancel. I get 2 Ce4 plus an Sn, makes Sn2 plus Ce3 plus. As far as who's the anode and who's the cathode, let's come up and label. This one's losing electrons, so that's our oxidation reaction. So that's our anode. And this is our reduction reaction. So that's our cathode. We've got ions in this one, so we can't have an electrode that has ions. And so I don't know anything about Ce. If you could find it in solid form, you could use that, or you could use an inert electrode. And then for this side, we could use tin for the anode. All right, line notation is just a shorthand notation for these electrochemical cells. And probably one of the reasons that I said earlier that 90% of textbooks put the anode on the left and the cathode on the right is because it matches this line notation. It's what you expect, anode moving to cathode. So what you do is you have a shorthand notation for what's going on with the anode, and you're going to look at those from left to right. And then for the cathode, you're going to look at its reaction from left to right. And what you have in the middle is what's, just representing your salt bridge. So if you have a solid electrode, then you use the solid. If you use an inert electrode, I'll show you what you do for those. So for this one, the electrochemical cells with zinc and copper. They tell you what the anode is. It's zinc losing 2 electrons, so it's your oxidation. And your cathode is copper gaining 2 electrons. So it's your reduction reaction. So the line notation, the anode goes first, the cathode goes second, and so look what happens. You've got zinc forming Zn2+. So you do zinc, single line, Zn2+. It's divided by your salt bridge. You show the salt bridge with 2 lines, and then look at your cathode reaction. Cu2+ forms Cu0. So you do Cu2+, single line, Cu solid. And so it really does give you a picture of what's happening in the reaction. It's very similar to writing the reaction out in a way, because you've got half reaction, and they're just separated by your salt bridge. So let's take a look at what we would do for A. Line notation, find your partners and see what's going on. We've got Hg2+ is forming Hg, and then we've got cadmium is forming cadmium 2+. So again, your first step with all these is to figure out who's being oxidized and who's being reduced. So Hg2+, to balance this, we would put the 2 electrons on that side. So he's gaining electrons, so he is being reduced. Cadmium is forming cadmium 2+, so its electrons would go on the product side. So this is being oxidized. And so oxidation occurs at the anode, reduction occurs at the cathode. So when I go to do my line notation, the anode goes first, the cathode goes second. So we've got cadmium solid, single line, forming cadmium 2+ aqueous, separated by a salt bridge. And then we've got mercury 2+ aqueous, single line, mercury solid. All right, for this one we've got Pb forming Pb2+, and 2Cr going to 2Cr2+. So notice what they said. They want platinum to be used as a cathode, because if you look, you just have ions, and so ions form. You're going to use a platinum or another inert electrode, like graphite. All right, so we've got Pb forming Pb2+. We need 2 electrons on the right. That's losing electrons, so it's being oxidized. And then we've got chromium 3+ forming chromium 2+. To balance that, I need an electrode or an electron on the left-hand side. So this one's gaining electrons, so it's being reduced. So lead is our anode, because that's where oxidation is occurring. And our chromium side is our cathode side. And of course, for the cathode, we're going to use platinum. So how that works is, nothing's different about the anode side. So we have Pb solid, single line, Pb 2+, and that's aqueous. Still divided by the salt bridge, but we're going to do this a little bit differently. Instead of saying Cr3+ single line, Cr2+, I'm going to say what happens, and then I'm going to do a single line and what the electrode is actually made out of. So here we would have Hg solid as our electrode. We don't have the luxury of a solid in this one, so we'll say Cr3+, we'll put an AQ, I just don't have space, comma, Cr2+ aqueous, single line, and then there's your platinum electrode. So that's what you do if you need an inert electrode. So the rest of the story, we've not really talked about, what ions are present in each side of the electrochemical cell or what's happening there. So we'll do a couple sketches for these examples, and so you can kind of show which way the salt bridge ions are going and how you calculate E naught. Alright, so here we go. We want it to be galvanic, and so we know that one of these has to be flipped. So if I flip the first one, I'm going to end up with a negative sum, and that won't be spontaneous or galvanic. So I know I have to flip this second one. So this is going to become 2Br minus forms Br2 plus 2 electrons, and E naught is going to be negative 1.09. Alright, we can go ahead and get our E naught cell for this. So E naught cell is equal to 0.27 volts. So a positive E, so that tells you that it is spontaneous. This one is losing electrons, so it's our oxidation reaction. Get rid of that one so we don't try to use it. This one's gaining electrons, so it's our reduction. So the bromine side is our anode, the chlorine side is our cathode. Now these are gases, they're not labeled, but chlorine gas and, well, bromine could be a liquid, I guess. And so the chlorine is actually going to have to be bubbled in, but for both cases you're going to have a platinum electrode. So we're going to sketch our two little beakers. We've got a platinum electrode on this side. We'll have another platinum electrode on this side. I'm just going to do my bromine on this side. So I have Br minus and Br2. And on this side I'm going to have my chlorine and my chlorine minus. Alright, so I draw on my wire, and it's important to know which is which because we know that electrons flow from the anode to the cathode. So I have to show that. So if this is my anode side, because it's my oxidation reaction, then electrons are going to flow from left to right. So that's showing the direction. Alright, for my salt bridge, I'm going to connect these, like I said, with a piece of filter paper, or sometimes it's like a porous disc, some way for these two cells to be connected. Alright, so we don't have to decide what our salt bridge is made of, but it will be an ionic compound, a strong electrolyte, that'll have plus and minus in it. So what it wants us to figure out is which way will the cation flow and which way will the anion flow. And of course we said there was an easy way to remember it, that the anion is always going to flow towards the anode, which is the left now in this picture, and the cation is always going to flow towards the cathode. But let's make sure we understand why. So if we focus on this left-hand side, what's happening is that Br minus is forming Br2 and kicking off 2 electrons. Those electrons are traveling through the wire, so they're not in the cell anymore. So what's happening is the Br minus is dropping. And we know if that negative charge drops, then the cell won't stay neutral. So to combat that, the anion from the salt bridge travels towards the anode. So that's why the anion in the salt bridge flows towards this cell. Alright, over here what's happening, if we look at the reaction from left to right, we've got neutral Cl2 forming 2 Cl minus. So the result is that this Cl minus is going to be going up. Again, you'd get a buildup of charge and your galvanic cell would shut down. So to keep that balance, to negate that negative charge, we need our cation to flow towards the cathode. So that's why it flows this way. So again, it's an easy way to remember that it matches, but you also need to be able to explain the why. Alright, we'll go quickly through this last cell, just making sure, I'll let you guys sketch it, making sure you know what's going on. Again, who do we pick to flip? It's got to be this first one, because that's the only way you'll get a positive number when you sum them up. So when I do E naught cell for this, you get barely spontaneous. You get 0.09 volts. Alright, and so if this reaction is flipped, we have Mn2 plus 4 waters forming MnO4 minus plus 8H plus 5 electron. So this is losing electrons, so this is being oxidized. That's our anode. And the IO4 minus is our reduction reactions because it's gaining electrons. So it's our reduction reaction, and that's our cathode. So if you sum, let's get rid of this one. If you sum those two reactions, you'll get the half reaction, and then you go ahead and you can sketch your cell.